To operate safely, an autonomous drone must understand both its own physical state and the surrounding environment. While multimodal large language models, or MLLMs, excel at static image analysis, they struggle in dynamic aerial settings. This video introduces UAV-DualCog, a benchmark specifically designed to evaluate MLLMs on dual cognition tasks. We will explore how this benchmark tests both self-awareness and environmental awareness across image and video modalities, revealing key bottlenecks in current AI models. Traditional vision benchmarks evaluate models using static, ground-level images. However, a drone in flight experiences continuous motion, rapid viewpoint changes, and varying target visibility. First, the drone must track its own position and motion relative to landmarks, known as self-state cognition. Second, it must understand the external environment's layout and target visibility, known as environment state cognition. Existing benchmarks rarely evaluate these two coupled dimensions together, leaving a critical gap in testing embodied aerial intelligence. The core breakthrough of UAV-DualCog is its Dual-Cognition Formulation. It evaluates models across 6 distinct tasks split between image and video modalities. For self-aware cognition, tasks include relative position reasoning and future observation prediction. For environment-aware cognition, tasks evaluate landmark directions and action decisions. Crucially, the benchmark goes beyond multiple-choice questions. It requires models to provide spatial grounding, like bounding boxes, or temporal grounding, like video intervals, ensuring the model actually understands the scene rather than just guessing. To build this benchmark at scale, the researchers developed an automated pipeline using scene-level semantic point clouds. First, they sample drone poses in a simulator and fuse LiDAR, RGB, and segmentation data into 3D point clouds. Second, they aggregate and manually verify candidate landmarks. Third, they generate executable flight trajectories under a hierarchical behavior framework to record first-person videos. Finally, they construct image-based question-answer pairs. This process yields thousands of highly accurate, verifiable samples with precise bounding boxes and temporal intervals. When testing state-of-the-art MLLMs, the results show a massive gap between recognition and grounding. While proprietary models like GPT-5.5 and Gemini 3 achieve moderate accuracy on multiple-choice questions, their spatial grounding scores remain incredibly low. For example, models often predict the correct relative direction of a landmark, but fail to draw an accurate bounding box around it. On video tasks, tracking landmarks over time and identifying complex flight behaviors remain persistent bottlenecks for even the most advanced frontier models. To demonstrate the benchmark's value as a training resource, the authors constructed a training split called UAV-DualCog Train from disjoint scenes. They applied a lightweight, 2-stage optimization probe on a small open-weights model, Quinn 3.5-4B. The first stage uses supervised fine-tuning to stabilize structured JSON outputs. The second stage applies Group Relative Policy Optimization, or GRPO, with a reward function targeting format, answer correctness, and bounding box quality. This optimization led to massive gains, with bounding box accuracy increasing by over 50 percentage points. While UAV-DualCog represents a major step forward, it has two main limitations. First, because it relies on simulated environments to ensure precise pose and visibility annotations, there is a sim-to-real gap when deploying these models on physical drones. Second, training models on static image tasks does not fully translate to video tasks. This uneven transfer highlights the need for future research to focus on explicit video-side supervision and cross-frame temporal consistency to align self-state and environment-state cognition over time. In conclusion, UAV-DualCog establishes a rigorous framework for evaluating drone intelligence from a dual cognition perspective. By forcing models to reason about both themselves and their environment, and requiring precise spatial and temporal grounding, it exposes the limitations of current multimodal models. The benchmark's open-source training data offers a clear path forward for researchers to fine-tune and build more capable, self-aware aerial agents.